Hi, I'm Zhuofan. Today, I'm going to introduce our work VisFIS, Visual Feature Importance Supervision with Right for the Right Reason objectives. My collaborators are Peter and Mohit, and we are from UNC Chapel Hill. Peter will take over the second half of the presentation. The problem we're considering is to make the models give correct predictions for the right reason by telling the model what features are important through additional supervision. And we're working on the VQA setting where, depending on the question, relevant visual features of the same image can be different. Here, we have human annotations highlighting which regions of the image are important, as shown in this example. Let's look at some model desiderata and how additional annotation helps achieve them. First, we want the model to give correct prediction given only sufficient features. We train models to predict labels given masked input of only relevant features. Second, we want the model to be uncertain given only irrelevant features. We regularize model prediction against uniform distribution given inputs of only irrelevant features. Third, we want the model to be invariant to irrelevant features. We first get model's feature importance explanation and then penalize any assigned importance to irrelevant features. Fourth, we want the model feature importance to align with humans. We achieve this by penalizing a distance between human and model explanations. We combine these four key objectives with the standard VQA task objective as our VisFIS method. We test our method on subsets that contain additional annotations of the three standard VQA datasets, Clever, VQA, and GQA. We also use the standard changing prior distribution shift to create in-distribution and out-of-distribution test sets. We mainly test on the classic up-down model, and for completeness, we also test on the newer Lexmer architecture. Here are the main accuracy results. We find that VisFIS is the best method across three datasets for both in-distribution and out-of-distribution accuracy. Other methods typically do not improve over a strong unsupervised baseline sub-random. The next best method is that of Singular et al., which improves over baselines only for the GQA dataset, but is still outperformed by VisFIS significantly.
Hi everyone, I'll be presenting the next set of results. Here we suggest a novel mechanism for why aligning human and model explanations improves accuracy. The issue is that model explanations are not necessarily faithful to model reasoning. So if explanations do not represent the model reasoning, why would aligning models with human reasoning improve accuracy? That is, why does improved explanation plausibility translate to improved accuracy? We check whether explanation plausibility for individual data points correlates with model accuracy, but we'll break this correlation down into groups depending on the faithfulness of the explanations. We find that models are more accurate when explanations are both plausible and faithful. This plot shows the relationship between accuracy and explanation plausibility at the data point level, grouped into three explanation faithfulness categories. We measure faithfulness using a standard input ablation metric for feature importance explanations. The results here are pretty stark. Plausibility correlates very strongly with accuracy, but only for faithful explanation. That's the orange yellow line. As faithfulness drops to its lowest levels, this relationship totally disappears, which is the flat green line. This means that plausibility on its own cannot measure the correctness of model reasoning. Plausibility only measures the correctness of reasoning when explanations are also faithful. We also further investigate right for the right reason metrics. One motivation for models being right for the right reasons is that this could improve our confidence that models will behave correctly on data that we can't test them on. We simulate this situation by computing right for the right reason metrics on in-distribution data and seeing how well they predict out-of-distribution accuracy. For the full results, we refer you to the paper, but the main negative result we observe is that these right for the right reason metrics do not actually correlate well with out-of-distribution accuracy, which is a surprising negative result for metrics. To recap, we want to tell models what features are important for solving certain tasks, and to do so, we use human explanations as supervision for model explanations. The results are that our VisFIS method improves both in-distribution and out-of-distribution accuracy on VQA tasks, and we hypothesize that explanation supervision improved accuracy by improving plausibility specifically for faithfully explained data. Lastly, we do not actually observe right for the right reason metrics to correlate well with model generalization. Okay, thank you for listening, and please feel free to reach out with any questions.